Hi there, I'm Jeff. Along with Alicia and Rohan, we're here to talk about the model DaisyWorld. DaisyWorld was initially created by James Lovelock, a renowned scientist. The DaisyWorld was a tool for him to prove his theory called Gaia. The Gaia theory essentially states that the Earth is one big organism and all the species within have a collective understanding of self-regulation to preserve life. He created a very simple world with no clouds, no atmosphere, and no water, only containing two species of daisies, as seen in the image here. So we have the black daisy with low albedo and white daisy with high albedo. Here we can see the findings from the original daisy world. The first graph shows the fractional area of the black and white daisies. The black and white daisies have different plant properties, resulting in the black daisy thriving at lower luminosities, and as luminosity increases, the black daisies begin to die off. On the other hand, white daisies thrive at higher luminosities. Here in the temperature graph, we can see the planetary, black daisy, and white daisy temperatures. All three variables follow the same trend. Here we can observe Lovelock's Gaia theory in which the black and white daisy work together to maintain the surface temperature of approximately 300 Kelvin, which is the optimal temperature for growth for both species. Lastly, we can observe that the planetary albedo is largely based on what daisy is currently growing on the surface. For example, as more white daisies grow, the albedo increases due to their reflective properties. Here are the different simulations that we conducted on the original Daisy world. First, we changed the albedos of the daisies. Then we added another daisy, the gray daisy. And then we added an ocean to mimic that of Earth. And lastly, we looked into the effects of radiative forcing. Next, we will talk about the results. There are two simulations created for when changing the albedos of the daisies. First, the black albedo was changed to 0.4 and the white albedo changed to 0.6, both albedos approaching neutral albedo. The two main observations here is that the area under the curve of the fractional areas are much less compared to the original. The other is that the 300 Kelvin constant line observed in the original is no longer seen. The other case is when the albedos are changed to extremes, 0.1 for the black albedo and 0.9 for the white albedo. Here we can observe an opposite effect from the first case. That is, the area under the fractional curves are much larger and the 300 Kelvin constant line is maintained much longer. Ultimately, by changing the albedos of the plants, the survival duration of the plants is affected.
Starting with the first plot, we can see that there are three lines now, one for the black daisies, one for the great daisies, and one for the white daisies. The temperatures and the planet albedo does not seem to change much due to the addition of the new gray daisies. Changes in the fractional areas are significant, which is justified because of the addition of the new daisies. Black daisy's area dies quicker, and the white daisy's area grows at larger luminosity values. To approximate a model like the Earth, we decided to add a body of water, which is the ocean. The ocean takes up about 50% of the Earth's area and absorbs a lot of light energy coming from the sun, therefore heating up the planet. Due to the increase in temperature, the daisy's population are not able to thrive, hence decreased survival lengths. The addition of radiative forcing does have a significant impact due to the amount of radiative forcing calculated. The high value is due to assuming that the concentration of CO2 in the atmosphere is 50,000 ppm. Although this value is unrealistic, it is used to show the trend. All three plots show similar profiles to the original with highs and lows at similar values as well, but due to the radiative forcing, the curve reaches their respective peaks and low points at lower luminosity levels. This makes sense because we know that the daisies survive best between certain temperature ranges. This DaisyWorld simulation can become even more advanced and more variables and parameters can be added to make a more accurate model of this planet. One major observation made throughout our studies was that adding an ocean variable made a huge impact because of its low albedo and the amount of area it covers. In the future, a variable for water vapor can be added because through our research, we read that it also has a drastic effect on the planet's temperature. Also, exploring predator and prey variables seems like something very interesting because they affect each other's growth and the growth of the daisies as well.